Welcome to our course on business analytics. Today we're going to explore some fascinating concepts that will help us make better business decisions. This is Chapter 12 of our coursework, and we'll be diving deep into linear optimization models. This chapter will introduce us to fundamental concepts that form the backbone of business optimization techniques. Let's get ready to understand how these models can transform the way we approach business problems. Let's begin with understanding optimization problems. These are powerful tools in business analytics that serve several key purposes. First, they can be used to support and improve managerial decision-making. Think of them as your analytical compass in the business world. Second, they always involve two key components: an objective function that we either want to maximize or minimize, a set of restrictions known as constraints. These problems can take two forms: linear or nonlinear. Today, we're starting our journey into prescriptive analytics, specifically focusing on how optimization models can enhance our decision-making process. Now we're looking at a simple maximization problem. This will serve as our first practical example of how to structure and solve an optimization problem. Let me introduce you to our case study, Par Incorporated. Par Incorporated is a small manufacturer of golf equipment and supplies. They're making two important business decisions. One, they've decided to enter the market for medium and high-priced golf bags. Two, they've secured a distributor who has committed to purchase all golf bags produced over the next 3 months. This scenario presents us with a perfect opportunity to apply optimization techniques to a real business situation. Let's examine the production process for golf bags at Par Incorporated Manufacturing. Each golf bag involves 4 key operations. 1. Cutting and dyeing the material. 2. Sewing. 3. Finishing, which includes specialized tasks like inserting umbrella holders, installing club separators. 4. Final inspection and packaging. Looking at Table 12.1, we can see the specific production requirements for each type of golf bag. These requirements will be crucial for our optimization model. Now let's look at the crucial numbers that will drive our optimization. First, the profit contributions. Standard bag, $10 per unit. Deluxe bag, $9 per unit. Then, the available time in each department for the next 3 months. Cutting and dyeing, 630 hours. Sewing, 600 hours. Finishing, 708 hours. Inspection and packaging, 135 hours. These time constraints will be key factors in determining our optimal production schedule. Now, let's examine each constraint in our Par Incorporated problem. We have 4 main constraints. First constraint: the number of hours of cutting and dyeing time used must be less than or equal to the available hours. Second constraint: the number of hours of sewing time used must be less than or equal to the available hours. Third constraint: the number of hours of finishing time used must be less than or equal to the available hours. Fourth constraint: the number of hours of inspection and packaging time used must be less than or equal to the available hours. Let's define our decision variables and objective function. This is where we transform our verbal problem into precise mathematical terms. Decision variables: let S equal to number of standard bags. Let D equal to number of deluxe bags. Our objective function: since Par makes $10 for every standard bag and $9 for every deluxe bag, total profit contribution equal to 10S plus 9D. Therefore, our objective is to maximize 10S plus 9D. Now let's write our first 2 constraints mathematically. Constraint 1, cutting and dyeing time, 7 over 10, S plus D less or equal to 630. This means the hours of cutting and dyeing time used must be less than or equal to the hours available. Constraint 2, sewing time, 1/2, S plus 5 over 6, D less or equal to 600. This ensures the hours of sewing time used doesn't exceed the available sewing time. Let's continue with our remaining constraints. Constraint 3, finishing time, 1S plus 2/3, D less or equal to 708. Constraint 4, inspection and packaging time, 1/10, S plus 1/4, D less or equal to 135. And don't forget our non-negativity constraints. S and D are greater or equal to 0. These non-negativity constraints are based on the logical fact that we cannot produce a negative number of bags. Let's put together our complete mathematical model for PAR Incorporated. Here are the objective function and constraints. Let's understand why this is called a linear programming model. The key characteristic is that both the objective function and all constraint functions are linear functions of our decision variables. What makes a function linear? It's a mathematical function where each variable appears in a separate term. Each variable is raised only to the first power. There are no products of variables. Now we're moving into the practical part, solving linear programs with Excel Solver. This powerful tool will help us find the optimal solution to our problem. We'll walk through the process step by step, showing you how to set up and solve this problem using Excel's Solver function. Looking at Figure 12.3, we see a spreadsheet model for PAR Incorporated. Let's break down its components. Rows 1 to 10 contain all the parameters for our problem. Row 14 contains our decision variable cells. Cell B14, number of standard bags. Cell C14, number of deluxe bags. Cell B16 calculates our objective function using SumProduct. Cells B19, B22 calculate department hours using SumProduct. This trial solution shows one standard bag and one deluxe bag as a starting point. Let's walk through the Excel Solver setup process. 1. Click the Data tab in the ribbon. 2. Click Solver in the Analyze group. 3. In the Solver Parameters dialog box, set Objective, enter B16. Select Max. By changing variable cells, enter B14, C14. Add constraints. Check. Make unconstrained variables non-negative. Choose Simplex LP method. Click Solve. The optimal solution from our solver analysis tells us: produce 540 standard bags. Produce 252 deluxe bags. This generates a maximum profit of $7,668. The solution shows we're using all available cutting and dyeing time, as well as all finishing time, as we can see by comparing cells B19 to B22 with C19 to C22. Finally, let's analyze the solver answer report shown in Figure 12.5. It contains 3 key sections. 1. Objective cell section shows our optimal total profit of $7,668. 2. Variable cells section shows the optimal values of our decision variables, indicates whether variables must be integer. 3. Constraint section shows left-hand side values, hours used, displays constraint relationships, indicates status, binding or not binding, shows slack values. For example, in the sewing department, slack sewing equals 600 minus 1/2, 540 plus 5/6 times 252 equal to 120 hours. This concludes our comprehensive analysis of the PAR Incorporated optimization problem. We've seen how linear programming can help make optimal business decisions using Excel Solver as our tool.